Right, so we've discussed the idea of the curl, and now it's time to move on to the other type of vector derivative that we can have. Now, when we talked about the curl, what we were really thinking about is the idea of a rotation. So if I had nabla times a vector field, or nabla cross a vector field, what I was really doing is I was looking at the vector field around a given point and seeing how much it curls around. So kind of seeing how much rotation we have. So you'd use the curl to determine if a fluid is rotational. So if you determined that the curl of a velocity field of a fluid was 0, then what you would have is you'd have something like this, where you'd have some sort of, I believe this is a laminar, this might just be constant flow across, because at any point you have no rotation. There's no rotation whatsoever. Lines move straight in these areas, so that should make a good amount of sense. So now it's time to move on to the other type of idea, which is the divergence. Now the divergence is a little bit different. It's in fact a lot easier than the curl to take, but consider having a vector field, say you have an electric field or magnetic field or whatever, and you want to determine for any one point how much stuff is going in and out of it. So what you do is you take around that little area, you kind of see how much flow, volume flow, takes place in a little differential volume that's so small we don't even give it dimensions. So around your point, how much flow is coming out and how much is going in. Now what that's going to tell you is it's going to tell you if that point is more of a sink or a source. So now what do I mean by a sink or a source? Well, what could happen is in a magnetic field, what I could have is I could have a dipole of sorts. Now the dipole would look like this, so it'd have field lines, magnetic field lines, that would kind of go around like that, and then some would go like way out here, some would just shoot out to infinity, but most would kind of go in between here, right? And then the magnetic fields might point that way, from left to right. And what the divergence basically says for this type of scenario is that if I have the divergence here, this divergence is going to be, this divergence is going to be telling me that the value is going to say, okay, well, you've got flow coming out. And then this will say, well, you've got flow coming in. So that's kind of the idea of it. Now, what's interesting is actually you can't have magnetic monopoles, so you need to have magnetic dipoles, which means that all sources must be paired with sinks. So you need to have the magnetic field lines need to be able to go somewhere. So they need to originate somewhere, and then they need to be able to end somewhere. And what you end up getting with this scenario is you get the divergence of your magnetic field is equal to 0, because you have no net influx and no net outflux. Anyways, that was a bit of a tangent. Why don't we continue on to our definition section? So consider a vector field F having the components of P, Q, and R, as we have considered for quite a while now. The divergence of F is actually quite simple. We just define it as the dot product between the nabla operator, and the nabla operator is the a vector of partial derivatives. So if I have partial x, partial y, partial z, and this operator is fairly meaningless while it's alone. It needs to be applied to something, so you can dot it with something, you can cross it with something if it's vector valued, or you can just multiply it if it is scalar valued, like we do with the gradient operator. Anyways, the divergence operator basically says I'm going to take the x derivative of the x component. I'm going to take the y derivative of the y component. I'm going to take the z derivative of the z component, and I'm going to add them all together. Now, what's interesting here is that you are not taking the partial derivative with respect to x of every component. You are just taking the partial derivative with respect to x of the x component. So it only wants it by component. So if you're taking the derivative of r with respect to y, you're doing something wrong. That would be incorrect. You just need to take it by components, which really makes taking the divergence quite simple. Now we can generate an interesting proof with this, which is that if I take the divergence of a curl, I will get 0. It's fairly interesting. So this is a result of the mixed partial derivatives being the same. So if I have partial, if I have the idea that the partial derivative of xy is equal to the partial derivative of yx. So if I take it doesn't matter which order I take the derivatives, they will be the same for the second order mixed. So anyways, when you take the curl and you apply the derivatives to them, you'll end up getting those mixed partial derivatives that are in fact the same. Okay, so thus they all cancel, right? So another interesting thing we can do is we can try dotting the, so this is interesting. If I have the gradient of a scalar function, I get a vector function. And then if I take the divergence of that, if I dot the gradient or nabla operator in once again, I will get a scalar function. So I'm going from a scalar function to a vector function back to a scalar function by applying the gradient operator twice to a scalar function. And what this ends up being in rectangular coordinates is partial squared f partial x squared plus partial squared f partial y squared plus partial squared f partial z squared. Okay, so that's fairly easy. I need to note that this is not true if I am dealing with a function in other coordinates. You may have noticed that in the partial derivatives unit, we did not cover spherical coordinates or cylindrical coordinates when we covered the gradient. Now, the reason for that is because those require extra add-ons. Now, if you remember when we did the multiple integrals unit, we needed to add extra things to our differential. We couldn't just do the integral over a spherical body, dr d theta d phi. No, we had an r squared sine theta that we needed to put in so that everything was normalized. Well, you need to do the same thing for the gradient. Fortunately, with Cartesian coordinates, you do not need to deal with that. With spherical coordinates, you need to multiply the theta component by 1 over r and the phi component by 1 over r squared sine theta. Okay, now that's, again, besides the point. We'll cover that in a later video potentially, but not today. Likewise, if I want to apply the nabla operator twice to the vector function, I will get a vector function again. Because I'm going from a vector function to a scalar function, then back to a vector function. So what ends up happening is I can rewrite that as the gradient squared of p, the gradient squared of q, and the gradient squared of r. Now, what's really interesting here is what this gradient squared means. We call it in physics, we call it the Laplacian, or in math, we call it the Laplacian. So we call it, if I ever see nabla squared, that is called the Laplacian. Now, there's a very important equation called Laplace's equation, which says that if I have this guy here, where I have the nabla dotted with nabla f, if that is 0, then we call that Laplace's equation. It's a very interesting concept that has a lot of roots in complex analysis, which is a very interesting subject. Anyways, let's continue with just an example. This is obviously going to be extremely trivial, finding the divergence of a vector function. Let f equal xz, xyz, negative y squared. Find the divergence. I got to take the partial derivative of this with respect to x, the partial derivative of this with respect to y, and the partial derivative of this with respect to z. Okay, partial derivative of xz with respect to x is z, partial derivative of xyz with respect to y is xz, and of course the partial derivative of negative y squared with respect to z is 0. So what I end up getting is I get z plus xz. So that's the divergence. So this basically says if I go to any point, right, any point in a vector field, how is the divergence going to vary as I go around the vector field, right? So that should be fairly simple. Anyways, that is all I've got for the divergence. In the next video, I'd like to consider Green's theorem again. So we didn't really cover Green's theorem for vector fields. We can reformulate it for vector fields, which is going to be very helpful for us. And at that point, I would like to kind of look at the idea of Maxwell's equations, which is a very important theory in physics. Electromagnetism. We'll consider the differential form of Maxwell's equations and Poisson's equation and what have you. And then maybe we'll look again at the idea of spherical and cylindrical gradients, although that probably won't be extremely important. You'll see that in physics again. And we will cover the spherical coordinates once again when we look at parametric surfaces. And then we'll move on to the fundamental theorem for divergences and fundamental theorem for curls. Anyways, that's getting ahead of myself. I'll see you guys in the next video. Thanks for watching.